thank you for the introduction. I will tell you about distributed interactive applications and how we can ensure automatic fault tolerance for these kinds of applications. As an example to illustrate, I'm going to show you our case study of a to-do list application, where a user can enter new to-do items. They're shown in the middle of this application, and they can be changed afterwards. This kind of interactions are very typical. They go back and forth between the user and the device running the application. We also have a distributed component to our applications, meaning that there's a set of heterogeneous devices that run parts of this distributed application. And there's also other users which may, for example, have their own state of their to-do list application. There's two things users do focus on in this kind of application. That's productivity and collaboration. Productivity means that the user wants to work on whatever their task is using the data they have available on the schedule the user has. So it's very important that the user drives this kind of interaction on their schedule. However, the user also wants to collaborate with other people in their group. They want to share their to-do list with their group such that tasks can be split and they know when some task has been done. So collaboration is also very important here. There is a couple of challenges in these systems. The first one is crashes. So a device of a user may crash. The user can then not work anymore. However, we assume that the device will be restored at some point at which the application should be fully functioning again, allowing the user to be productive again. Crashes always also cause disconnects in a distributed system, meaning that now we have multiple users that are still working on their own local replica of the application. However, they can no longer communicate, they can no longer collaborate. There's nothing we can do about not being able to collaborate during a time of a disconnect. However, we assume that at some point the disconnect will be restored and collaboration should be able to continue seamlessly. The last problem is in the interactions themselves. In a typical application, applications can ensure their guarantees, their consistency by driving the execution of the application. However, in these interactive applications, the user drives the control. So the control is inverted back from the application towards the user, which makes ensuring guarantees quite hard. If you want to know more about this kind of application, there was a great essay at Onwards presented yesterday called Local First Software by Ink and Switch, and you may really want to read this essay. It's great. So we've been also looking into automatic fault tolerance that is already ensured by existing systems such as Apache Spark and Flink. In these systems, you basically define your computation as a data flow graph in a functional language, and the system takes care that your computation is executed in a distributed system correctly, no matter what kinds of failures you have. However, to do so, the systems need control of all the devices in the distributed systems. So when something fails, they can re-execute computation on a different device. They can start up a new device. This doesn't work in our use case because if I'm collaborating with my supervisor and her device fails, then I cannot just replace my supervisor. This doesn't work. So the question is, how do we provide automatic fault tolerance in our kind of environment where we don't have this kind of control? And the solution is going to be a data flow graph of connected reactives, which I'm going to talk about next. So reactives are our basic abstraction to structure applications and will ensure automatic fault tolerance. As a bit of history, so yesterday the Flapjacks paper won the most influential paper award for OOPSLA 2009, and our abstraction, our reactive abstraction, is directly influenced by that paper. So I'm very glad to be part of that legacy. So let's look again at the to-do list application and the state of a single device. We will divide the to-do list application into three reactives, R1 to R3, which will represent the input, the middle layer, and the output of this device. So as for the input, we have a source reactive, which has an initial state V, which will so the initial state corresponds to the current input of adding a new to-do item, which at the beginning will be empty. From this from this new item the user can input, we want to derive the list of to-do items, and we do this using a fold reactive. So we fold R1 using an initial state, which will be the empty list for this example, and a folding function, f, which will add the new item to the list of to-do items. And finally, this is just the internal state of the applications, which we want to display to the user. So we map the state of R2 given the function g, which will display the state to the user on the device. For the distributed part, there's a second device which basically runs the same application with the same directives, but we replicate the innermost directive, so the directive containing our list of to-do items R2 using CRDTs. And I'm going to go into detail about this works in a second, but first let's look at how state changes are, well, how the duration of state changes works in detail. So we're looking at these two nodes, R1 and R2, and how they behave over time. So this is the same two nodes, same states, and they start in initial state V and an initial state I for R2. When R1 is changed by the user, so entering a new to-do item, there's a new state W, which will automatically cause the derived directive R2 to change accordingly, applying the update function f to its prior input I and the change of R1 W. If there's another change x, again apply f to the prior state and x, and so on, and so on, and so on. So all these changes, when an input directive R1 changes, then the derived directive changes at the same time. This also results in the fact that, and this is a bit important, so please remember, you can recompute the state of R2 using this sequence of changes. If, yeah, you can recompute the state using the sequence of changes. So now let's take a step back and look at propagation of changes in larger graphs, which we do provide a lot of guarantees for, which together will provide automatic fault tolerance for these applications. So here's a larger graph, same concept as before. These are all reactives derived from each other. A user can make a change to one of the input reactives, which will be propagated through the graph along the colored nodes. In the paper, we prove many important properties. So first, we prove determinism, which means that if in a certain state of the graph a user makes a change, this will have the same result all of the time if it's the same change. We also prove isolation, which means that if a user does two changes at the same time where the first change is not yet fully propagated, the propagation of the second change will not interfere with the first change, resulting in consistent applications. Third, we prove precision, meaning that we know perfectly well which reactives are connected to each other, and we do not have to re-evaluate reactives that are not connected. This is fully automatic. You cannot depend on a reactive without depending on the value, and you cannot not depend on something when you read the value. Fourth, we prove concurrency. So if there's two directives derived from the same input directive, and that input directive changes, but the two derived directives are not in any relation to each other, we can show that our algorithm allows to evaluate them in parallel, which our implementation does. Then we prove glitch freedom, which is a property that's well known in reactive systems such as flapjacks, which for us basically means that this single node here, which is reachable on multiple paths from an input, is only evaluated once, not once for each path, which would produce spurious values called glitches. And finally, we prove eventual consistency. So why eventual consistency? Well, the problem is that if we have a disconnect, we can no longer propagate a change to a remote device. There's just no way to do this. But we still want to apply the change locally because we really, really want availability. We want the user to be productive and be able to modify its local state. So the other device will get inconsistent because the changes are not applied. This is a classical result of the Kapp theorem, saying that we cannot have availability and consistency at times of partitioning. However, so to ensure eventual consistency, we're using CRDTs, and Traditionally, if you use CODTs, there's a bit of a problem because they have a restricted set of operations you can execute, so you may not be able to fully express your application semantics. However, in our model, we can express everything that we can express in our model using CODTs, and this is what I'm going to show you. So what we're going to look at is the input sequence of this replicated node, which is currently disconnected. So we're looking at two replicas of the input over time. So here again is the two devices, A and B, they're disconnected, and time again flows to the right. So if changes, for example, to replica A, which is a change X, we may have a concurrent change to replica B, which is change J, and these changes are not related over time at all. This means that the systems are currently not consistent. We can have more changes on B and A, which are related to the prior changes on the same device, right? And what happens if at some point we do reconnect and there's another change, then this change will actually be related to the changes on both replicas. So we get here again a partial order that says in which way the user perceived the changes to have happened. And then the same happens for device A, again extending the partial order with a change where all changes are now related to each other. As I said before, this was the part I hope you remembered, we can derive a consistent state of a derived directive if we have a total ordered sequence of changes of the input directive. We here only have a partial order, but using existing research on CODTs, we can show that this can always be extended to a total order without any coordination. Basically, there's multiple strategies. For us, we use the simplest one and order concurrent things just by the replica ID. So all changes of A, if they are not otherwise ordered, come before all changes of B, resulting in this order X, Y, J, K, L, Z. Using this total order, we can compute the state of the derived directive consistently for all devices. So let's go back to our data flow graph where these nodes have become inconsistent. Using the CODT, we can merge this replicated device, which means, well, we can merge the replicated reactive, which means this single reactive will now be consistent. However, in many applications, there's a problem that if you now read the value of a CODT, it may still be an inconsistent change, and you depend on this inconsistency, producing, deriving a new state which is also inconsistent. This can never happen in our programming model because every time the CODT changes, everything that read the value of the CODT is also automatically kept consistent using the same propagation strategy that we have shown before. This results in, based on the eventual consistency of the CODT, we can always show that the full application is automatically kept eventually consistent. We've also done a performative variation. I'm going to illustrate again using our to-do list case study. So what we did is we measured the computation time and the network overhead for adding a new item to the to-do list. We compared our system with a strong, consistent implementation and a completely inconsistent implementation. Obviously, the inconsistent implementation is faster, and we use a kind of a baseline of where we want to push performance. We're not quite there yet. However, we do beat the consistent implementation both on computation time and on network overhead. In the paper, we do have many more things I didn't talk about to not make the talk too long and not overwhelm you. We do prove that we can restore the data flow graph after a crash in a fully consistent manner. We do support fully dynamic graphs, so you can change the graph at runtime, which is very important for adding and removing nodes from a distributed system. We do support nested reactives, so you can contain reactives inside other reactives, sending them over the network, and they will be automatically connected. We have our small step semantics on which we do all of our proofs. We do talk more about the implementation in the paper, and if I forgot to mention your favorite system that's related to this, it's probably also in the related work. We have a very extensive list of related work. You can find our implementation at rescala-lang.com. You can try it out. You can play with the examples. You can read the manual. You can write bug reports. And I've shown that for this case of distributed interactive applications, we do provide productivity and collaboration, even though we have the challenges of distributed and interactive systems. We do so using the data flow graph combined with eventual consistent CODTs, which we can make fully automatically and then also propagate changes fully automatically, resulting in a completely consistent overall application. Thank you very much for your attention.
I have a quick question. So in the picture that you show here of the two replicated devices, you show a single link in between the two.
You mean?
What do you have on the last slide?
This one?
No. On the very last slide, you show a single link between each device. So those are the two nodes that are kept consistent using CRDTs.
Yes.
And nothing else is. So yes. I guess my question is, I guess it's up to the programmer to decide that these are the two nodes that need to be kept consistent.
Yep.
And are there interesting kinds of bugs that can happen if they pick like the wrong one? For example, had they picked the map instead, you would have had consistent views but inconsistent state.
So I guess interesting bugs can happen if you synchronize. Obviously, if you synchronize two little things, then your application will not be replicated at all, right? Because you just didn't replicate something you assumed to be replicated. The other way around, you can always replicate too many things. This will cause additional network overhead because more things are replicated, wouldn't need to be replicated because they're just derived. Usually, you only replicate fold directives because they're the only ones that do keep state. Map directives can always be recomputed locally. However, sometimes it's interesting to replicate a map directive from like a central device to many other clients in a broadcast fashion. So there's then only one central point of change. This is also fully supported.
I had a question about, you said you proved eventual consistency. Which properties did you prove and how did you do that?
So basically we rely on the proof of strong eventual consistency for existing CRDTs. Right? So this is something we did not reprove, we just assume as a premise. Well, there's proofs for that. And what we do is kind of, given the properties of a single CRDT, basically all of the derived directives inherit the same consistency level as that CRDT they depend on.
Okay, and then one last one. So you basically order the operations totally when there are two concurrent sequences happening, right? Mm-hmm. Have you thought about that it's kind of arbitrary, so you may end up in a state that is really weird or even violating some invariance? Or
okay, so I think this is something I should clarify a little bit because I simplified for the slides. So we can always semantically use these arbitrary, like the arbitrary ordering of sequences to get a consistent state, which obviously is nice for the proofs because you can say, well, we are always eventually consistent. However, if you want specific semantics, like if you want a certain way of merging, you can always provide your own CODT. Especially if, for example, your fold node is just a map or just a set. There's very efficient CODT implementations for those, and you can just use them and skip the whole sequence and thing. You just directly synchronize the state of these two things. So the user is always free to pick their own semantics in case of consistency.
Great. So let's take one last question.
Thanks for your talk. Yesterday's speaker mentioned that one of the hard parts was actually picking the right network technology to synchronize your devices in a peer-to-peer fashion. What did you pick for your work?
You mean the networking layer?
Yeah, the actual networking technology. Yesterday they mentioned that they used WebRTC or peer-to-peer, or, well, it depended on their projects, and that made a huge change apparently to the usability.
So basically, we base our work on work of my colleague Pascal, who's in the audience, and we have a basic messaging abstraction, so you can send messages between devices, which is then executed on whatever runtime we need. We do support TCP, WebRTC, WebSockets, and did I forget something? Okay. So mostly reliable direct connection protocols. For our case, WebSockets and WebRTC are very important because many of these applications run in a browser context. TCP works perfectly fine for server-to-server communication. We didn't have that many problems with WebRTC, but we also didn't try very complicated setups, I guess. But basically any packet-oriented protocol would work fine for our cases.
And is that messaging API you use available somewhere? Is that messaging API you use featuring
yes,
all?
Yes.
Yeah.
So you probably can find it from our website, maybe. Otherwise, it's I think Scala Loki on GitHub.
Cool. All right. Let's thank the speaker again. And the final talk.